Just wait another minute. We'll see if anybody else joins us. I hope that's the case. I know Julia said that she could make it. Madison, I know you had responded, and obviously you live with Maria, but I might send a quick text message out to at least Connor and Allie that I have their contact information. If you guys have any way of contacting Olivia or Lee, um, just to make sure that we connect with everybody so that they know that there was a time change and we're an hour earlier here.
Yeah, I just texted Lee and Liv. They're gonna be on soon.
Oh, perfect. Perfect. All right, let me make sure to text Connor and Allie here. Actually, I don't have my phone handy. Do either of you have Connor or Allie's cell? If not, I can go grab my phone. I just don't have it on me.
I don't have Allie's number, but I texted Connor, so
Okay.
he'll
And
also be on shortly.
yeah, all right, perfect. All right, there's Julia. Let's wait another minute. Madison, you said that you did text Connor and he was going to be on.
Yeah.
Okay, I'll just wait another minute and then we'll go ahead and get started. All right, there, perfect. There he is. All right, trying to get myself comfortable here. Have you guys had an okay break? I would love to see your faces there. Julia says yes. Madison, oh, thumbs, I love the thumbs up. How about Liv, Connor? Did you have a good break? Maria, did you have a good break? Were you gone, Maria? Did you go home? No, you were here. Yeah, so here was my break, and at some point I will show you guys pictures. So every day over break was spent either with another orthopedic surgeon or getting an MRI or whatever. And Connor, you'll appreciate all of this related to soccer injury. Sam ended up having surgery. We were in the hospital all day Thursday for that. So I have just been like playing nurse at home to deal with that. And then Daisy decided she wanted to go into heat. So that's been fun. So I have a dog in heat at home, which she hates wearing a diaper. That's just like loads of fun. So there was that. Um, and then the past 4 days, I have been dealing with, you guys know what kidney stones are, right? Like I don't have kidney stones, but you can get similar kinds of stones in your salivary glands. And so I have had a blocked salivary duct, which meant like this side of my um like like it was like a golf ball was in here. And like every time you tried to eat, because then you tried to like produce saliva, it would swell and it was so painful. And this morning I passed that stone, and it is just like I'm glad it was over break because then I didn't have to worry about like taking time, but I've not had a break. Yeah, it's been just not fun. Now Sam's on break next week. Barron is on break next week, but we still have to like he's not allowed to be weight bearing. He cannot get up and walk anywhere. So yeah, it's a lot right now.
This
So
is not your semester.
it is not. It is not. I've been yeah, sick a lot. I don't know. Maybe indication that stress and lack of sleep and poor eating, and yeah, I'm not practicing what I preach to you guys, and I'm case in point. Oh, and there's also and you guys will know about this at some point maybe because I'm going to try to write a case study on this. Um you guys know I wear my heated vest. Like I love that heated vest. Maybe you see me wear it sometimes. Well, apparently that has created too warm of an environment and created um, an infection on my back. And so the microorganism that is living there produces an enzyme that inhibits tyrosinase, and tyrosinase produces melanin. So the reason I noticed it was I'm like, what are all these white splotches on my back? So yeah, this is just another page in the book of Dr. Parenti falling apart in spring 2025. But because I was doing some research as to how this infection works, I'm like, oh, we learn about tyrosinase. Maybe I'll write a case study on it for students to learn about. All right, enough about like my crazy break. I'm glad you guys gave thumbs up. That was good that you had good breaks. Okay, so first, and I'm going to put this in the chat just so that I have it. It'll save with this Zoom. It'll sort of save the chat because I want to remember what we talk about. Remind me again of times that have worked for you guys to take the exams. So I know, Madison, I think you had said 2 p.m. on Monday. Was that when you wanted to do it? So I'm just going to put these in the chat. I'll hit enter in a minute and you'll see all of them. So 2 p.m. Monday was an option. Now, I think some people were now interested in 2 p.m. on Tuesday potentially because if you previously were taking 410 and you know you have that free, that works. So 2 p.m. Tuesday. Is there anybody on this call? And I guess 1, 2, 3, 4, 5, 6. Who do we not? Oh, Allie. I know Allie will have 2 p.m. on Tuesday probably free because that she was a 410 student. Between those two times, 2 p.m. Monday or 2 p.m. Tuesday, does that handle all of you guys? Time works for that? Okay. So I will make sure to circulate that back out. So exam, whether you take it Monday or Tuesday, will be on your learning units 3 or 4. So I am going to circulate, and I'm going to share my screen with you guys. Go through and we'll talk about some documents here. I have not yet shared this out with you guys, but I will, and this is the one from last year. It's not going to be any different. The date will change, but this is kind of giving you the structure of how the quiz questions go. So there is detail on the citric acid cycle, and I'll let you know that this is the last metabolic pathway that we study in this level of detail. So it's really only glycolysis in the citric acid cycle. And so there's these questions that are going to ask you details with those 8 steps, enzyme names, substrate product names, cofactor names, structures that you may need to draw. And so here's the first question. NADH is produced in these reactions. And so for this version of the exam, it says, and if there's a number that I'm looking for, it will tell you how many. So there's 4 enzymatic steps where NADH is produced. So, and I'm asking for the enzyme name. So that's what you'll want to list that's there. So there may be times where there's clues where I'll tell you like how many answers there's supposed to be. Okay. So that is sort of that detailed question about the citric acid cycle. Then there's another question that's dealing with more glycogen metabolism. So this again is citric acid cycle stuff. This is glycogen metabolism. Now we really didn't do a lot with enzyme names and so forth, but we did learn about the three, well, I should say there's only 3 steps of enzymatic breakdown of glycogen or synthesis. So for example, the first question that you see in this category, and these are only, again, it's 14 points for this, 14 points for this. B vitamin is required for phosphorylasis chemistry, okay? And this enzyme name, and this is the cofactor. So this is, you list what the B vitamin is, and then you'll tell me what that B vitamin is. Like we've had with previous exams, you'll have 10 minutes at the end that you can have access to your notes. So that continues to sort of be an option. But those are the first 2 questions. And again, we're going to look back at notes and homework and things like that and give you guys, and the study guide, and give you guys an opportunity to ask questions. So those are the first 2. Those are sort of the detail ones. And then these are, when I say more big picture, there's details that are there, but they are more big picture, thinking about glucose homeostasis. So this is maybe thinking about the structure of glycogen. And I'll show you like a homework question where if you were to see a structure of glycogen and were to point to certain things, like is this a reducing or a non-reducing end? What's the linkage that you see here? Think stuff like that. If you were to see a structure of glycogen, that you could label those pieces. Thinking about the steps that we learned about for gluconeogenesis. Now, 7 out of the steps are just reversals of glycolysis enzymes, but then there was 3 glycolysis enzymes that were far equilibrium that we needed to make sure to find alternative pathways for. And then we had sort of those slides, I'll make sure to point them out to you, where we talked about the differences between muscle and liver cells. Okay, and then there was also that flow chart, that cascade flow chart. And we'll look at both of those slides, thinking about how the enzyme pKa as a master phosphorylator can participate in glucose homeostasis, and then thinking about glycogen storage disease. Now, I will tell you for this one, and I'll point out from slides in our case study, I want you to be able to think about, as we understand glycogen breakdown or synthesis, if you were to have this enzyme in a patient be either activated or inhibited, what might you expect to see with regards to glucose homeostasis? You know, would you see that that patient is hypoglycemic or hyperglycemic? Would you expect that they'd have an enlarged liver or not? Would you expect that they'd have abnormal glycogen structure or not? So I'll sort of show you where that is. Again, that cascade flow chart, we'll make sure to point it out. Keep in mind, this year it was asking about a high blood sugar scenario, and then the next question was asking about low blood sugar. You might see the flip of those, where you might see the cascade flow chart dealing with low blood sugar. And then when you think about tissue-specific responses, again, muscle versus liver, you might be asked a question about high blood sugar. So make sure that you understand that these are highlighted here too, because those words might change. And then there's sort of like 22 points of what I call laundry lists, just kind of like concepts that we've learned that don't specifically relate to those categories that we discussed above, maybe talking about the Warburg effect and what that is and what it relates to. Again, we'll talk about this as we sort of go through our study guide. Thinking about the fates of important branch point metabolites that we've learned about. To this point, we've really learned about 3. We've learned about acetyl-CoA. We've learned about pyruvate as the endpoint of glycolysis. Again, acetyl-CoA is the starting point of the citric acid cycle. And then oxaloacetate is an important intermediate in the citric acid cycle and an important metabolite that's necessary for gluconeogenesis. And then we've learned about almost all of the vitamins that you had to learn about last semester, but now we've sort of discussed where we see them in metabolic pathways. So think if you were to have, and I know there's a homework question that asks you to like put all of this in one spot, like, you know, what are the B vitamins that you know about? What do we call them? What are they used for? And so forth. And I will say, there are going to be, moving forward with exams, these questions that tell you to think outside the box. They're a question that you've never seen, but it's a question that you have learned enough where you could apply your knowledge and answer a question. Okay? They're not worth a lot. Okay? 4 points out of 100, so don't stress about it. Okay? They will start ramping up a little bit more with our next two exams where you'll see that you'll have to answer a couple more of them, so it'll be worth a few more points. But it's just asking you to think about things that relate to either the citric acid cycle or glycogen metabolism and ask you questions on it. Okay, so 4-point question for that. There's going to be a list of questions you can choose from. It's not just one question. But you'll have the ability to do that. Now, when I say there's 2 bonus question opportunities, that is saying if you answer more than one of those questions, you could answer an additional 2 of those. And if you get those right, you can get some extra points for answering those ones right. You have to tell me which one you want to answer for like your full one. And then you can pick ones that you say, I want to try this one for bonus. Okay, so those are again questions that you haven't seen at all, but they're related to content that you've learned. So I'm going to pause for a second there, see if you guys have any questions on this. I haven't circulated this out to you yet, but I will make sure to circulate that out right after we're done here, along with the recording link. And if there's anything else that comes up here that we need to make sure to share out that I haven't shared with you guys yet. Any questions yet?
I have one about 4, and I need to pull up the homework to ask it, I think. Because there were 2 cascades that we had to do for the homework, one that in
Ah,
synthase and like phosphorylase, and then the other one didn't. So
yep.
which
It is not the one that deals with F26P.
okay.
It is
Okay.
the main one that deals with the phosphorylation cascade that deals with glycogen breakdown or glycogen synthesis. Okay, and Julia or no, that not Julia, it was Maria. I think you just asked a question about um, using your notes. Yes, you will have at the end of when you're done and you want 10 minutes for your notes, you have 10 minutes for your notes. And again, you can have as much time as you want for the exam. I will be around. I may need to have someone else because I think I have a dentist appointment. I have to go in for this or not tonsil, salivary thing. I have to go in and see my dentist and make sure that I don't have an infection from it. And that's on Tuesday at, I think it's at 1:15. So I should be there by 2. If not, I'll just have somebody get you guys started and I'll be there shortly. And I think that was the only questions that we had. I'm going to stop sharing for a second because I'm going to find some other things to pull up for you. I'm going to pull up the study guide that we're going to have. Let's see. Exam 2 study guide. And I'll make sure if there's anything on the study guide that is stuff that you guys don't have to know because I've taken it out and so forth, that will I'll let you know that. So pull that up. I'm going to pull, let's see, I pulled up homework for both of these. Okay. Any questions on stuff while I'm just pulling up a few pieces of content here for us to sort of go over? All right. Why don't we'll start with the study guide and I'll just sort of go through things. I'll let you know if there's anything to take off the study guide. Let me start sharing my screen again. All right. You guys see my screen? Okay. So, and a lot of these things we've sort of talked about. Reminder, when you see these study guides, these usually highlight homework problems that will sort of refer you to the specific content. So when we talk about glycogen breakdown or synthesis or gluconeogenesis, semi-detailed questions about the steps of these processes. So again, think, knowing enzyme names, substrate product, cofactor names for glycogen breakdown or synthesis. And then for gluconeogenesis, since that's really, for the most part, reversal of glycolysis, that's sort of one that I still want you to know. So a few homework problems, we'll look at those in a minute that allow you to sort of practice that. Thinking about sort of the net equation for glycogen breakdown. So remembering that it's essentially a phosphorylasis sort of chemistry. Cofactors are substrates that are necessary, you know, why we need PLP or UTP. Again, we'll look at a homework question and we'll look at notes sort of for that. Homologs. Remember, anytime in the notes you sort of see something that refers to a homolog, that's kind of reminding you like, hey, we've seen this before, and a reminder of where we've seen it. So we'll kind of highlight where that's the case. Specific products, understanding that, you know, we produce both G1P and G6P. Then we need to dephosphorylate to generate glucose. If we're doing synthesis, we need to activate that glucose monomer. And then being able to think about the linkages that are involved in glycogen, whether it's an alpha-1,4 linkage to make our sort of homopolymer, or those alpha-1,6 branch points. So this is highlighting that this is stuff that's in the notes. So I'll sort of point that out. Rate controlling steps. So again, when we're talking about glycogen breakdown, it's phosphorylase. Glycogen synthesis, it's synthase. So remembering what those are. And we'll see this as well when we look at the citric acid cycle, be able to think about and name sort of the kind or type of chemistry that's happening. Is it phosphorylasis chemistry? Is it hydrolysis chemistry? Are we talking about acetal or ketal formation, right? That's the formation of that glycosidic bond, or again, breaking that bond. Why do we need to activate monomers for sort of coupling? We'll look at that. Anytime we see functional group migration, those enzymes are going to be called mutases. So think of some of those classic things that we see. We'll look at some enzyme active sites that maybe we've discussed, and then highlight if there's amino acids that have unique roles or typical roles that we've seen. Again, this is looking at the structure of glycogen, you know, be able to think about the different residues that we see there, what's the linkages, whether they're reducing or non-reducing ends. So I'll go through and I'll highlight slides that are important for you to put a little asterisk next to. Mechanism, again, we've have some mechanism pieces. The notes are there. Again, if you feel like mechanism is not something that's sort of your forte, I wouldn't stress about it. It's something that you're never going to see, you know, an exorbitant number of questions or points that are on it. But, you know, it is something that's part of what we learn about in the course and learn to apply that knowledge from last semester here. So I'll kind of highlight where that feeds into content here. And then for gluconeogenesis, right? Thinking about how it's essentially a reversal of glycolysis. So many of those names, enzymes, or chemistries are going to be reversals of what we learned about in glycolysis. Needs for cofactors or co-substrates, right? Thinking about the need for biotin, vitamin B7, and bicarbonate if we're going to be adding CO2. The specific products that are produced in gluconeogenesis, right? We've got oxaloacetate and phosphenylpyruvate. Those are sort of the main products that we get by reversing that 10th step. And then the net goal of gluconeogenesis is to produce glucose. So rate controlling steps for gluconeogenesis are the same as the reversal of the rate controlling steps for glycolysis. So PFK is for glycolysis, and then FBPase is for gluconeogenesis. Types again of reactions. This is something that I want you guys to be working towards, because as we get towards, let's say, the final exam, there's a good chance I'm going to show you maybe a type of chemistry. I'm going to show you metabolites that are interconverted, and I want you to be able to look at things and tell me what's changed. Was it an oxidation or a reduction reaction? You know, would you be likely to see NADH being reduced or NAD plus being oxidized to facilitate that chemistry? Sort of that's that high level sort of piece that I want you to be able to do. So think about that as you're looking about and learning these types of reactions. If you were to see it in the future, how would you know that it's a carboxylation or a decarboxylation reaction? What B vitamin might be required for that? Those sort of general themes that we see. I'm going to go through sort of this content on glycogen metabolism. That'll probably go over to the homework, and we'll look at the slides for a little bit. And then we'll move on to the citric acid cycle. When we think about regulating pathways, right, in general, we've learned about regulating enzymatic pathways by regulating the activity of an enzyme. But this is just a reminder that you can control the availability of an enzyme by upregulating transcription or translation rates, or sort of modifying enzyme decomposition rates, but that's not sort of the focus of what we're talking about. We're generally focused on activity, but I think this homework question is just a reminder of that. Reminder of the two main ways that we learn about controlling enzyme activity: structural allosterism, which is binding a small molecule to change between T state and R state; covalent modification, adding or removing phosphates. And often these two work together, where if you add or remove a phosphate, it also changes R state or T state. So those pieces often go together. The global umbrella of phospho versus dephospho system, understanding that a phospho system is a need state, dephospho system is a fed state. And again, how that relates to the importance of maintaining blood sugar, right? We call that glucose homeostasis. So that idea of top down, you have two ways that you can break down a glucose polymer, either by eating a glucose polymer, a starch, or breaking down your own animal starch, that is glycogen. Or again, bottom up is gluconeogenesis. So these are sort of those general pieces to think about with glycogen metabolism. And then this is getting into specifics about glycogen. So thinking about, again, that cascade, we've got pKa, we've got phosphorylase kinase. And so those are phosphorylase, I'm sorry, are kinase enzymes. And then thinking about phosphorylase is the last enzyme that's responsible for sort of breaking things down. And calmodulin really is related to phosphorylase kinase. So phosphorylase kinase is the alpha, beta, gamma, delta, and then delta is calmodulin. So I'll make sure to point that out in the notes. This is a little bit confusing here because it makes it seem like those two things are together, and they're not. But we learned about the master dephosphorylator, that's PP1. And then we just talked very generally the rules and rationalizations for glycogen branching. So again, it's probably going to be helpful when we look at a slide or talk about that homework question to sort of deal with that. Julia, this sort of gets at your question, thinking about F26P. And so that is not a cascade you need to know in detail, but I do want you to know that F26P is a fed state signal. So knowing these pieces and knowing, okay, glycolysis is a fed state pathway, and if F26P is a fed state signal, if you upregulate F26P levels, you're likely to be upregulating glycolysis, things like that. And then we spent some time learning about the malate aspartate shuttle as it connects a little bit here to we saw the ability to have that participate in shuttling and getting oxaloacetate out for gluconeogenesis, but it also connects to content that we learned about with the citric acid cycles. So we'll tie that in again in our next learning unit there when we look at that information. We talk about pathway integration. Again, big theme that we see in this course is thinking about glucose homeostasis, high blood sugar, low blood sugar. So this is thinking about those phosphorylation cascades. This is thinking about the difference in cell types and what they do. And then this is thinking about need state and fed state pathways as they relate. Sorry, I'm trying to highlight here, as they relate to glycogen breakdown or glycogen synthesis. So we'll spend a good bit of time here kind of highlighting where those slides are and where those are important. And then we talked about glycogen storage disease. That's from our case study. And then when we started talking about gluconeogenesis, we were highlighting and starting to introduce this concept of we've been living in the cytosol with previous metabolic pathways that we've been discussing. But gluconeogenesis has one enzyme that lives in the mitochondria. Do you guys remember which enzyme that is? Which enzyme lives exclusively in the mitochondria? We need it for gluconeogenesis. Julia, I love watching your face because you get so excited and you're like, I think I know this.
Is it pyruvate carboxylase?
Yes. You know what I so want to do with you guys? I just want to play like biochemistry Jeopardy with you, like have trivia. Like that would be the best way to study with you guys. But yes, it's pyruvate carboxylase. And because we have an enzyme, this is the first enzyme that we've seen that requires us to dip in the mitochondria. We need to sort of think about cytosolic versus mitochondrial locations for things. So I'm going to pause there for a second, see if you guys have any questions on the study guide, and then I'm going to go over and we're going to look briefly at homework, and then I'm going to flip through slides to sort of talk about Unit 3. All right, so let me look at homework here. So let's go over here, and you'll see here on this first part of this homework key that a lot of this is review. It's just reminding you that we've learned already about how to regulate enzyme function by activity or availability mechanisms. We learned about structural allosterism or covalent modification. We've learned about phospho versus dephospho states and these top-down versus bottom-up approaches. So I'm not going to kind of go through those because I think you guys hopefully still remember those, and that's should be review from previous stuff. When you think about sort of glycogen breakdown or glycogen synthesis, I want you to think about sort of those 3 steps. We learned about them with sort of a general name, whether it was mobilization, debranching, or mutation. And then we did learn the specific enzymes. I'll show you where those slides were, and then specifically what happens in those steps. Let me actually go, it might make sense to sort of go back and forth here, reminding us of sort of where we have. So this is again that big sort of picture, that 30,000 foot view. I'll come back to that slide. These are the slides that I'm talking about where it's like, hey, in one word, what happens at this step? You know, what's the enzyme that is necessary there? And what does that enzyme do? You know, whether it's cleaving alpha-1,4 glycosidic linkages or this bifunctional enzyme. Or we're doing mutase chemistry. We're moving a functional group, and we've seen lots of cases where we're moving phosphate groups as functional groups. So let's see, this is the equation, right, that we see for glycogen breakdown. It's phosphorylasis. So we're just breaking that glycosidic linkage, but we're using phosphate rather than water to do that lysis chemistry, which means we're not getting free glucose, we're getting glucose 1-phosphate. This is the enzyme active site, sort of showing us the importance of having vitamin B6, so that's PLP. And interestingly enough, you might say, hey, there's phosphate chemistry that's going on here. I'm using phosphate as a nucleophile to do that hydrolysis chemistry. Maybe it's from PLP. Well, actually, nope, it's not, right? PLP is used actually as a general acid and general base to deprotonate that phosphate to actually allow it to eventually become nucleophilic. So first, we're going to actually protonate our glycosidic oxygen from this phosphate, where we're going to have PLP acting in this case as a general acid. And then in the next step, and I would never expect you to remember this if you didn't have this picture here. So for any of these things where we see enzyme active sites sort of doing stuff, I would never expect you to know the details unless you had the picture. You're clearly not going to have a lot of the words that are there, okay? But you might see an enzyme active site where it might be asking sort of questions. This learning unit was the first time we saw a bifunctional enzyme. So that's an enzyme that has 2 chemical functions. But in this case, it's a bifunctional enzyme where both stores are open, right? We're going to see 3 examples of enzymes that have more than one function. This is a bifunctional enzyme where both stores are open. We're going to see a little bit later, and this has to do with that F26P story, Julia, that you asked about before. We're going to have phosphorylase and kinase, phosphatase and kinase activities that are the bifunctional activities on that same enzyme, but only one of those stores is open at a time. And then the last thing that we see with an enzyme that can do more than one thing is pyruvate dehydrogenase, which that is not like a mom and pop 2 stores. That is a mega mall. There's like 3 different stores and like lots of stuff that happens. So again, that bifunctional debranching enzyme does 2 things, moves limit branches and then hydrolyzes residues. So a lot of these questions are asking, I'm going to zoom back out here so I can see all of this. Function of phosphoglucomutase, right? So again, this is a homolog, kind of indicating we've seen functional groups like phosphates being moved to different positions. The homolog that we see here is when we saw phosphoglycerate mutase. So you might be asked to sort of compare and contrast things in that regard. So that is some details through question 9. You know, starting here, 5, 6, 7, 8, 9 sort of deal with glycogen breakdown. And then you see sort of a similar set of questions. And I'm going to apologize right now if the numbers for problems might be different. Sometimes I don't rewrite my keys. I take questions out. But you guys I know are smart enough to figure out, oh, that's the same question. But when we start here with question 10, it deals with glycogen synthesis. So reminding us about those 3 steps in the enzyme names, why we need to, do activation chemistry. And then here's this question I said I was going to highlight. When we think about adding in branches, there's 2 things that we need to consider. When we add a branch, that's a good thing because we increase the ability to mobilize glycogen rapidly. Because the more branches we have, the more ends we have, the more non-reducing ends we have to chew in and break down glycogen. The problem is if you have too many branches, then you can't pack a lot of glucose in because it gets too compact. So I want you to be able to think about that, those competing sort of forces, if you will. One thing that wants lots of branches, one thing that doesn't want as many branches, and you land on this sweet spot in the middle. That is what nature really landed on to generate the branching patterns we see in glycogen. Certainly may see some pictures of enzymes like this where you may be asked to label certain pieces, right? And this is a compare and contrast. So pKa and phosphorylase, the catalytic subunits of each of those, have very similar structures. But highlighting, and we've learned about this in class, this is really a phosphomimic, right? Phosphorylase has a glutamic acid that replaces the threonine. So it really looks like a phosphorylated threonine residue. So nature has made a phosphomimic, which means this enzyme can never be turned off. If pKa could be turned on and off by phosphorylating or not, that threonine 197, phosphorylase is always going to be on. And remembering, right, we do this a lot, phosphorylase is going to be, um, um, uh, oh, this is phosphorylase kinase. I should have another word there. Phosphorylase kinase is the one that has 4 subunits that are always hanging out together, and they change their shape. pKa has 4 subunits, 2 alpha, 2 beta, but they physically separate. I'm trying to do my Spock thing here, right? They physically separate in order to allow my catalytic subunit. So compare and contrast how these 2 kinases do their chemistry. Now, this is sort of getting at, Julia, that, and this is a large sort of picture of that same slide. I'll make sure to highlight it in the slide. The 2 things that are really important and kind of summarize things are this phosphorylation cascade slide, and then this slide that looks at the differences between the muscle cells and the liver cells. Those are 2 really important slides. There's going to be lots of questions that are sort of derived from that. So be able to think about both of those systems as it relates to high versus blood sugar. Again, I'll show you where those slides are. Even though this is a homework question, this is the same content, just shown with another picture. Okay. So I'm going to zip over real quick just to the slides here and remind us. My computer so wants to restart. I'm getting a spinning wheel that makes me very nervous. This slide, which I know was super scary to many of you when we started, when you just looked at it and you're like, this is a lot of information. But once we walk through it, and again, there's a video that's available if you need to hear it again, you're like, oh yeah, I learned about all of this. This slide just puts it all in one place, right? And then we did the same thing here. And I told you guys I didn't go through and edit these slides. A lot of times these are just ones where it's like, this is the slide I had from the previous year, and then here's the new one. Content isn't necessarily different. It's just maybe I added a couple more things. But this is another important slide reminding us of things like the important hormones or chemical signals that are found in your bloodstream, who responds to them, whether it's muscle cells, liver cells, or both. Thinking about how glucose transporters are different between these 2 different cell types. And again, thinking about why muscle cells, there's like almost like a 3-part system that ensures muscle cells never help with a low blood sugar. First of all, they never listen to the signal. Second of all, even if they broke down glycogen into G6P, they cannot snip the phosphate off of G6P, so they never can export it. And even if they did, number 1 and number 2, if we're in a low blood sugar, there's not going to be the insulin sensitive glucose transporter that's there. So be able to sort of think about answering those questions like, why would a muscle cell never be able to help with low blood sugar? Those are the 3 reasons why. Let's see. I think that actually could be, and a lot of this is just like repeats of the same, and my key here. The last thing I'll sort of talk about here is, and Julia, this is the question you're asking about. Understanding aspects of this cascade are important, but you're not going to like have to recreate sort of this one. What was this other picture here? This is thinking about, and we already answered the question, pyruvate carboxylase happens to only live in the mitochondria. So if you are doing gluconeogenesis chemistry, let me go back to our notes here. If we're doing gluconeogenesis chemistry, right? Since we have to live in the mitochondria for this, there are 3 pathways. So be able to think about these different pathways that you can eventually get out to finish gluconeogenesis in the cytosol, right? There's well, just stay in the mitochondria the whole time until you get to phosphenylpyruvate. There's a door for that. So you have to think about things that there's doors for. You are likely to see a question, and I know there was a question, I think, on your multiple choice quiz that you had, asking like which of these metabolites does not have a door to pass freely between the cytosol and the mitochondria. So this again is asking you to think about that piece. How do we do mitochondrial chemistry, but then eventually get to have phosphenylpyruvate in the cytosol, which is going to be the starting point really for gluconeogenesis by reversing glycolysis. So I think that covered everything that I wanted to talk about on the homework. I'm going to see if you guys have any questions on sort of the homework key or looking at your homework. And then I'll just flip for a second through our slides, and then we'll sort of wrap up that content on glycogen metabolism. I'm going to go back to the notes for a second here. I'm just going to go back to the beginning, and I'm just going to see if there was any slides that I want to make sure to draw particular attention to. This slide's obviously an important sort of big picture slide. Highlighting things that we've already talked about, sort of high level. I will say, like slides like you see here are likely to be content that you want to sort of get ingrained in your brain, because that's going to not only repeat itself through future learning units, but you're likely to see content like that for your final exam. High level 30,000-foot view. Like when you go to study for your final exam, I would recommend going back and looking at videos that are labeled 30,000-foot view, because that's the level that you're going to need to know things for the final. Oh, I want to draw attention to this slide because there was one thing on your study guide that talked about glycogen structure. So if you were to see like this picture down at the bottom here, that you could label all the pieces that we have here. You could label where anomeric carbons are. You could label reducing versus non-reducing ends. You could label alpha 1 4 linkages and then alpha 1 6 branch points, right? Anything that we've sort of labeled on here, you might be able to label if you were to see a blank version of that picture. So that's what that study guide question means when I say glycogen structure. We talked about this slide, sort of the higher level overview of both glycogen breakdown and glycogen synthesis, right? And then we went into a little bit of detail. So here again, we looked at on the homework question, this is the only sort of enzyme active site that we've really looked at here is for glycogen phosphorylase. When we talked about the chemistries that happen with some of these enzymes, like that bifunctional enzyme for glycogen debranching, we've got movement of functional groups, right? This is a reversible enzyme. And then, let's see here. And again, I think I've got duplicate slides here, so I apologize, but when I was trying to finish up lab that day and I wanted to make sure to get things out to you, I didn't edit these. So you may see repeats of the same content. And then this is going through thinking about glycogen synthesis. So big picture, I want you to remember too, anytime we are making any type of a linkage, we make bonds, and we might like make, that's kind of a stabilizing thing. It takes energy to break bonds. When we make bonds, we get energy, But still, to do that carbon-carbon bond forming chemistry, or in this case, an oxygen-carbon bond forming chemistry, we generally need to do some activation so that we have something that's a good leaving group. We create good nucleophiles and electrophiles. If something's a really good nucleophile, something's a really good electrophile, that means it's reactive. It's not likely to do the chemistry that we want. So we're going to see this theme a lot, that we're going to add something only to subsequently remove it because it's a good leaving group, and that's going to generate a good nucleophile or a good electrophile. We talked about the kind of concepts here with maximizing storage space and mobilization speed with branching. This is sort of getting at all of that enzyme regulation sort of piece. Glycogen phosphorylase, we studied the structure of that already. pKa, we studied the structure already. Phosphorylase kinase is the new one. So you want to be able to think about and compare and contrast those guys. And I was reminding you guys, calmodulin really is one of the 4 subunits of phosphorylase kinase. It's calcium dependent. And then we didn't spend time talking about this picture here. So don't worry about this picture. The words down here are what you really need to know. And this is one of those times, there's only 2 that we're going to learn about, where we have something that's a little bit weird, right? Insulin stimulated protein kinase. That seems a little bit weird. Oh, Dr. Perrone, I thought when we were doing phosphorylation chemistry, that meant we were need state. Why is it under fed state? Well, the connection is that it's still stimulated by a fed state hormone, even though the activity that it's doing is kinase. Okay. But I want you to remember that PP1 is a master dephosphorylator. pKa is a master phosphorylator. And then these get into those slides that sort of have our cascade. Let's see here. And then we talked about the differences in tissue types. We talked about gluconeogenesis and the importance of generating oxaloacetate, right? Because once we need to generate oxaloacetate in order to generate phosphenylpyruvate. And then there's the details of where things are located. So we've done this. So Julia, the big piece here is sort of, and it was a great question that you asked. I'm not going to be asking you specific questions about the F26P sort of cascade, but I do want you to remember that it's a fed state signal, which means it should activate glycolysis and inhibit FPBase. And logic checks are going to sort of hold true there, but this is not a slide you really need to know the details of. And then we get into, I would take a look at, and again, if you're like, mechanism is just forever going to be Greek for you, maybe don't spend time focusing on it, right? It is a part of this course, and it's something that I want you, I hope that you'll learn. But if you're just like, it's not worth the amount of time that I need to put into it to understand it well, then don't. Or come see me, and I'll try to help you as best I can. But here's where we saw applications of mechanism, right? When we are doing cleavage of glycosidic bonds, that's taking an acetal or a ketal, generally an acetal because we've been talking about glucose as an aldose sugar, and breaking that linkage to generate still a closed ring sugar. So it's still a hemiacetal or a hemiketal, and then that free alcohol. So breaking a glycosidic bond is hydrolysis of an acetal. So we've got chemistry of that there. Formation of glycosidic bonds is actually forming an acetal. So this is reviewing sort of the generic chemistry that we talked about last semester, and then sort of seeing application to it. All right, now this whole, and I literally had not gone and edited. There's like way too many slides here, but it's talking about glycogen storage disease. I'm going to highlight for you, here's the only thing, because everything was really still an application. Here's the piece that I want you to know. Okay. And we build on this actually in our next learning unit, but I want you to think about, if you need glycolysis to continue, what do you do with pyruvate? So there's things that we talk about in the citric acid cycle learning unit that have to do with what are the 5 things that we know we can do with pyruvate. But we can convert it to lactate. We can convert it to alanine. Those are both ways to deal with the buildup of pyruvate from glycolysis. And then we can say, liver, you go and handle this mess. And so we can take the alanine and export it to go back to the liver, or we can take the lactate and export it to go back to the liver. We're going to learn more about those cycles. That's the Corey and the Cahill cycle. So I would say this was sort of an important slide to be able to think about. This starts building us into thinking about the relationship between different alpha keto acids and their corresponding amino acids, right? So you should be able to sort of match or pair those up. There's 3 that we've learned about so far. And let's see, there was one other slide I wanted to show you here. And it looks like, yeah, there's just duplicate slides here that I just did not have I didn't take time to go through and edit out. Looks like there's even duplicates of stuff from you guys. Put a little star by this slide, okay? I don't, you're not going to be expected to like remember or repeat this verbatim, but I would want you to think about for enzymes that we've learned about. You don't need to remember like the name of the disease or anything, but for example, if you were to think about somebody who has a deficiency in liver phosphorylase chemistry. Okay, so that means phosphorylase. Phosphorylase breaks down glycogen. So in my liver, if I can't break down the glycogen that's there, I would expect that my liver is going to get big because I'm accumulating too much glycogen because I can't break it down. And if the purpose of having glycogen in my liver is so that I can put it out to the bloodstream when I have low blood sugar, that means this patient is likely to have hypoglycemia because the liver is not able to help with low blood sugar, right? So that's sort of when we relate sort of disease states, I might expect you to think about the enzyme and what it does, and that what you might expect to see from a symptom standpoint in a patient. Okay. So, think about that sort of moving forward as we learn about enzymes, particularly if they might be enzymes that relate to sort of glucose homeostasis. So you guys have this in your slide deck. I think honestly, the rest of these are just slides from previous years' students. So like, yeah, this is last year's students. It was Abigail and Ellie and so forth. So they're just sitting in here, but the content is no different than what you guys learned about. So I just did not, what was this? Oh, somebody's screenshot. So honestly, same slides. So most of these slides you can sort of ignore at the end. Okay, I'm going to pause for a second, see if there's anything you want me to go back to, talk about a little bit more. And of course, you can come see me tomorrow, Tuesday. If you've got questions, send me a message. All right, let's zip over to, let me go back to my study guide. A little bit of a shorter section now when we think about citric acid cycle. Half of this content here in the citric acid cycle, we did talk about a lot of it in lab, but here's the content that you need to know for lecture. It is something, whether it's pyruvate dehydrogenase or the actual citric acid cycle, it's the last time that we're going to study detail of enzymatic steps, substrate and product names, structures, cofactors, things like that. This was another learning unit where we had a fundamentals quiz. So citric acid cycle was a fundamentals quiz, just like glycolysis was. So just as a preview and a heads up, when it comes to your final exam, you need to know your fundamentals quizzes again. Like the level that you needed to know glycolysis for your fundamentals quiz, that's the level that you need to know for your final exam. Not like all the enzyme names and things like that. That sort of level of stuff. So think about it as I test you on it with fundamentals, like that actual fundamentals quiz. You're going to see questions related to it on this exam. And then third time's a charm, hopefully, that you remember it when it comes time to for your final exam. So this is again all of those same types of questions. I'm not going to take the time and sort of run through this laundry list, but you do need to know pyruvate dehydrogenase chemistry and the citric acid cycle to a pretty deep level. We really didn't talk too much about pathway regulation. I'm actually going to look at this in your notes, and this may be something that we're going to sort of cross off, and I'm going to tell you you don't need to know. So I'm going to take a look at your notes and see what's there and remind myself and you what we sort of got through. But we really didn't talk too much about regulation of the citric acid cycle. Let's see. Pathway integration stuff. So how do we think about this? Again, just this concept of being able to look at metabolites. I mean, many of you, whether we talked about it in lab or you saw my research students sort of give their 410 presentations, you should be able to look at metabolites and see how they're related. Did it lose a carbon atom? Did it change redox state? And be able to think about sort of what's going on in that regard. Anytime you're doing redox chemistry, you're probably going to see an enzyme that's called the dehydrogenase. Important branch point metabolites, we talk about fates of pyruvate. And then when we're doing the citric acid cycle, right, we're talking about acetyl-CoA as sort of the starting point. Oxaloacetate is an important branch point intermediate that's synthesized in the citric acid cycle, but we do not siphon oxaloacetate off of the citric acid cycle, right? Pyruvate carboxylase is going to be how we make that if we need it for something like gluconeogenesis. And then I'll highlight, we're going to look back at notes and see sort of what we talked about with this. I would probably say we're at least maybe a 65-35 split between learning unit 3 and 4. Just because we do so much with the citric acid cycle in lab, I don't do as much in lecture. We did talk a little bit about the Warburg effect and thinking about how that can affect mitochondrial processes. So I'll sort of show you where that comes in with the notes. And then remember I told you there was one question I sort of wanted you to know about for your quiz on the glyoxysome. I want you to remember the name of that organelle. We know, then I've told you, like you guys cannot convert fats into glucose. I want you to remember that. Like hands down, you can't do that. And the reason you can't do that is you don't have this special organelle. We did not go into the details for how it happens, but I do want you to remember the name of that organelle. It's a glyoxysome that allows select organisms that have that organelle to synthesize glucose from fats, which normally is not able to happen. Okay, so pretty short sort of piece here. Again, it's probably a 65-35 split in terms of content. Let's take a look at the homework here. Again, this first question on the homework is actually just your fundamentals quiz content. Okay, so that's not really important. Do know this is one of those things that we went through details for pyruvate dehydrogenase chemistry. So we went through that in class. Again, there's a video that's out there if you need to rewatch that on thinking about how this megamol, if you will, really works. Again, learning about 4 pyruvate dehydrogenase chemistry, we see 4 of our B vitamins involved there. Oh, excuse me. We see different sulfur chemistry. So be able to compare and contrast the different sulfur chemistry. We talked about this when we went through this this sort of picture, that you might have sulfur chemistry that has to do with actual thiol residues on like an organic molecule versus thiol residues that are on an amino acid. So be able to think about how those are different, but fundamentally it's redox chemistry. And think about the different kinds of sulfur chemistry. I'm going to look at our notes because I think they're a little bit more detailed than I have on my key here. I want you to think about the kind of chemistry. Is it trans-thioesterification? Is it disulfide exchange? What kind of chemistry is sort of happening there? This is just meant to be sort of a study guide as you're learning about, the 8 steps in the citric acid cycle. What is the substrate? What is the product? What's the enzyme name that interconverts this substrate and product? What's the chemistry that's happening? And why do we do this? And again, the reason I go through sort of those purposes is the hope is, okay, now I understand the story of what's going on and it's easier to remember what happens. I mean, truthfully, guys, that's how I had to learn it myself in order to be able to teach it to somebody. Because if I'm just memorizing stuff, it's hard to just speak about it sort of comfortably and conversationally. So, again, try to learn it as a story in that way. Um, let's see. This is just, again, the homework is often meant to be a way to compare and contrast or put similar kinds of topics together. So for example, this question really says, hey, here's all the redox chemistry we've learned about. Where did you see that? And what functional groups are interchanged, right? So this is all stuff that involves NAD plus NADH chemistry. So what's happening with all of these? So again, in a way to sort of do a meta-analysis, if you will, of redox chemistry with vitamin B3, for example, that we've learned about so far. Actually, this is not something we really talked about. So you probably can cross off question 8. It's not in our notes. Looking at it here, I know I didn't talk to you about it, but this actually talks about how we activate pyruvate dehydrogenase. So we didn't talk about pyruvate dehydrogenase regulation. So you can take that question off. And we really didn't talk about, I would say take question 9 off. We really didn't talk about this. We didn't talk about regulating the citric acid cycle. At some point I might get to it in lab, but don't worry about it for lecture. We did talk about this in lab, and I do want you to remember that that last step, malate dehydrogenase, has a large negative or large positive delta G, which means it's an unfavorable process. We don't make very much of the product, and we couple it with the next reaction in the citric acid cycle to pull that forward. So 10 is definitely a fair game question because that's something we've talked a lot about. Again, question 11 here is kind of like we saw with question 7, just sort of a meta-analysis of, hey, what are the possible things we know we can do with pyruvate thus far, right? So that's that piece. And this question 12, I'm going to sort of highlight, there's a better way to sort of think about this. It's the fates that we talked about for pyruvate that are potentially related to and using citric acid cycle chemistries. Okay, so I'll point to that slide when we see that because I think it's easier to see there. Question 13, and I think some of you asked me about this when you turned in your homework. Don't worry about question 13 here because I did not go through the glyoxylate pathway with you. The only thing I want you to remember is there's a special organelle called the glyoxysome. If you want to do this chemistry, you want to make fats into glucose, you need to have that organelle. But don't worry about the details of this pathway. Let's see. And this is again, we sort of did this in lab, right? This is just a reminder of why when we have things that are substrates or products for one reaction and substrates for a next reaction, that's the assembly line concept. But that's stuff that we've really talked more about in lab. So you're not really gonna see any questions on that here. And then this question 15 really relates to, again, something that we even saw more when we talked about gluconeogenesis. How do we start with pyruvate, do chemistry that's required to happen in the mitochondria, like pyruvate carboxylase chemistry, and then eventually get out to do gluconeogenesis? So I would say that this question is even more related to content that we did and flipped out in Learning Unit 3. So that was the homework there. Any questions on this or ones that you want to ask about? Hopefully I've addressed ones that are like, nope, you don't need to know that.
So do we not need to know 14 then?
Um, the way that you need to know 14 is because you need to know the structures of stuff in the citric acid cycle, and you need to know that it's a circle, it's a cyclic process. These 3, this is step 8 and this is step 1. They're connected by virtue of it being a cyclic process. So I wouldn't say you don't need to know this, but we've talked about this both in lecture and in lab. I know I'm not answering your question, Madison, very well. So yes, you sort of need to know it, but I think you already know that question. Anything else on this? And then I'm going to take just a second. I know we started a little bit late. I don't want to take too much more time here. Not a lot of slides here, and I think some of these are even duplicates here. I want to let you know what you need to know from the citric acid cycle. This is, again, one of those 30,000 foot view slides. We are always going to start our learning units moving forward with sort of these big picture ones. And I'm going to encourage you, as you at some point study for your final exam, it's really only going to be these first few slides that are going to be the high level things that you need to know. But why I'm bringing up this slide as well is I do want you to know that these are the two things that are the hallmark of cancer cells that are referred to as the Warburg effect. Now, not every cancer cell does this, but there are ones that exhibit these features, and it's decreased oxygen consumption and increased lactate production. Now, why that happens is that we're clearly not doing a lot of mitochondrial aerobic chemistry, which means we're not consuming oxygen. And because we still need to recycle NAD plus in order to keep doing glycolysis, we need to do lactate dehydrogenase chemistry. So that's sort of, this was, again, should be largely a summary and a review slide of things we've talked about. But I will say, and there's a video out on this slide, this is a good slide to sort of review when it comes time for your final exam as well. Again, those are just highlighting the two hallmarks of the Warburg effect that I do want you to know those. Here's where just your fundamentals quiz questions. We spent a good bit of time sort of talking about and doing a pathway walkthrough here. First half of the pathway, again, is to do chemistry on our substrate, which is generally producing a little bit of energy, but getting rid of 2 carbon atoms as carbon dioxide. And then the second half is doing some functional group reconversion or conversion to take succinate and convert it into oxaloacetate. So good bit of time talking about that. I do want you guys to know, be able to look at a molecule and say, is that an alpha keto acid or is it a beta keto acid? And I know you don't look at, let me zoom in here, you don't look at isocitrate and say, that's a beta keto acid. But it is one step away from being a beta keto acid when I oxidize that alcohol. So, some of those sort of big picture things. So that was a slide there. That's actually your fundamentals quiz. Put a little star by this slide, right? This is all the details for pyruvate dehydrogenase. So again, video is available for you to watch on this. If you're looking at this and you're like, I don't remember a lick of this, I need to review that. You can rewatch a video on this slide. And then we did a lot of time walking through the citric acid cycle without looking at individual steps. Okay. And I will highlight, I would hope that if you were to look at some of these pictures here of things that are going on, you could piece together, given the arrows that are here, oh, this is a bond that's forming. You know, be able to look at pictures and see things that are happening because you might see an enzyme active site that's related to things that we've done here. That was on your last exam, right? Where you could see, if you chose to do that question, right? You saw the enzyme active site and you had to describe what was going on. So I'm not going to take the time right now because I want to move forward here. But this is sort of walking through, like we did for glycolysis, the different, and I did say this is definitely an enzyme active site sort of chemistry that don't worry about. But for these 8 steps, how do these 8 steps work? Okay, so you will see details on those. Now I will say, don't worry about this slide. Okay, we didn't talk about regulating the citric acid cycle. It's a little bit different to think about regulating the citric acid cycle because it's a cycle. So all of those rules that we use to apply for glycolysis, where we say, well, it doesn't make sense to have the last step because it's the last step, right? Well, that doesn't apply when you have a circle. So I still want you to remember, if you're looking at delta G values, you're looking for large negative delta Gs. Those are going to be ones that are going to be likely control points. But we really didn't talk about this here. So other than understanding that fundamental principle, there's nothing else that you need to understand here. I'm going to get to this later on, talking about this ratio of NAD plus and NADH. This is a really important fuel gauge. Don't worry about it right now. Okay. And then there were some slides on things that, like I didn't go over that slide, so just obviously ignore that. This slide is one that's sort of put a little star by this one. This just reminds us of the different ways that we can use citric acid cycle enzymes to help us think about doing things either in a need state with pyruvate, for example, if we need to do gluconeogenesis, or a fed state with pyruvate. So for example, if we need to store that excess energy as triglycerides in adipocytes. But you'll notice we start out with pyruvate and we sort of use enzymes of the citric acid cycle. And notice I said we didn't go through the citric acid cycle. We may just use citric acid cycle enzymes. And this is sort of the key to some of the concepts for what we do in lab is understanding that who malate dehydrogenase chooses to interact with is going to determine what kind of chemistry it's doing. And we're going to get into more of that in future learning units. But this is sort of a slide that has a lot of stuff that we've talked about, but I want you to think about the fates of pyruvate there. And then I think this is the last slide that probably has content that I want you to know on it. I want you to know these relationships. These are the 3 amino acids I had said before. I want you to know 3 amino acids and their sort of connected alpha keto acid skeletons. So oxaloacetate and aspartate are related. Alanine and pyruvate are related. Alpha ketoglutarate and glutamate are related. Okay, we're going to learn a couple more later on, but those are the 3 that I want you to know right now. We can interconvert them by transamination chemistry, which is what's highlighted in orange here. Now, we didn't go through any details as to how that happens, but understand that that's one way we can do that. And we see those enzymes in our metabolic panels. You see ALT and AST. Those are transaminase chemistries that happen in the liver, and they tell whether your liver is functioning or not when you can do these chemistries. And then we're going to learn about this a little bit later, this reductive amination process, but that's a way that you can interconvert alpha ketoglutarate and glutamate. So that's all that I need you to know from this slide. And that might actually be all that you have to know. I'm going to flip through the rest of these slides here. And yeah, there's nothing else you need to know from here. Okay, so even though I threw these slides in here, I literally just copied and pasted everything that I had in my slide deck from Learning Unit 4 and said, here's this. But after this 25th slide here, and there's even ones that are duplicates before this, you don't need to know anything. Okay, they're just slides that are in my slide deck that you don't need to know. Questions? And I don't want to keep you guys too much longer. I usually like to keep these to an hour.
Okay, this might be a stupid question. However, can you show me how to show the difference between an alpha keto acid and a beta keto acid?
No, that is not. And you guys know I will always tell you this. There's no such thing as a stupid question. And if you ask a question, there's a good chance that someone else has that same question, or someone else will be like, I was a little bit fuzzy on that. I feel better now because it's clarified. So I'm going to show you as an example of this slide where I highlight in red and blue alpha keto acids and beta keto acids. So if we look at the structure here, oh, damn it. So it's called an alpha keto acid or a beta keto acid. I'm going to do it with this sorry, I'm like frantically flipping through slides because I want to find certain structures. Let me try zooming in again over here. Okay, so let's take pyruvate, for example, right? I would expect you to know the structure of pyruvate. Come on. All right, let me try to zoom in and not zoom in too much. Okay, structure of pyruvate is right here. Okay. Anything that's an alpha keto acid or a beta keto acid is going to have a carboxylic acid functional group. That's right here. Carboxylic acids are always the highest priority functional group. So they are carbon 1. So that's where we sort of start labeling things from. So the alpha, beta, gamma, those always refer to positions 1, 2, or 3 away from the highest priority functional group. Okay, so this is the acid functional group. So this is the alpha carbon, this is the beta carbon. An alpha keto acid, keto meaning ketone, has a ketone functional group on the alpha carbon. Okay, if I come down here to alpha ketoglutarate is also an alpha keto acid. Here's the carboxylic acid functional group. At the alpha position, I have a ketone. So let's look at a few molecules that are beta keto acids. And I'm going to flip back here really quick because I think in this learning unit, nope. I'm going to go all the way back to the beginning here because we talk about them here too when we look at the structure of oxaloacetate. Okay, let me look here because here's also where we sort of talked about it. Oxaloacetate. Now, maybe this could be a little bit confusing because oxaloacetate is simultaneously an alpha keto acid and a beta keto acid. Because it just depends on what carboxylic acid I'm talking about. If I'm talking about this carboxylic acid group is a beta keto acid because not on the alpha carbon, but on the beta carbon, I've got a ketone. Following? Now, if I circle and highlight this carboxylic acid group, this one is an alpha keto acid. But in general, we refer to oxaloacetate as a beta keto acid because we're talking about this carboxylic acid as the one that comes off as CO2. Does that help? I think oxaloacetate can get confusing because it's simultaneously an alpha keto acid and a beta keto acid, depending on which carboxylic acid you're talking about. Okay. Let me go back here just to the citric acid cycle. So the reason we have to move this hydroxyl group in citrate to make isocitrate is this is going to be the carboxylic acid that comes off in the first carbon dioxide that's eliminated in the citric acid cycle. Okay. Now you might look here and is isocitrate an alpha keto? And I'm just going to ask you, Madison, just because you're the one that asked the good question. Is isocitrate an alpha keto acid or a beta keto acid?
Didn't you say that one was like a special hidden thing?
Right. Actually, isocitrate is neither, but I'm going to say that it's a hidden beta keto acid. Because if this group was not an alcohol, but it was a ketone, do you see that now, if I talk about this carboxylic acid group, beta to it is a carbonyl, as a ketone. Do you see that? Now it's really weird, right? Because I've got 3 carboxylic acid groups on isocitrate. So it's like, well, which one am I getting rid of? You're getting rid of the one that you can get rid of. And if I can make this into a ketone, that means I've made a beta keto acid and I can get rid of this CO2 group. Does that make sense? Sort of. So if we look at the next slide, here's isocitrate. If I do redox chemistry, and I would hope that you guys could look and say, oh, if I take an alcohol and make it into a ketone, that's oxidation chemistry. Oh, so my B vitamin is reduced. But if I take and I oxidize this alcohol to a ketone, I've got a beta keto acids. Beta keto acids easily decarboxylate. That's going to tell me that I can get rid of this CO2 molecule. And then I'm left with alpha ketoglutarate. And Madison, sorry, I keep putting you on the spot, but you asked the good question. What is alpha ketoglutarate? Is it an alpha keto acid or a beta keto acid?
Alpha keto acid.
Right. Now, again, I'm not talking about this carboxylic acid group because that's not anything. I can't get rid of this CO2 group. I can get rid of carboxylic acid groups as carbon dioxide if they have either an immediately adjacent ketone or 2 carbons away ketone. Now, if the carbonyl, if the ketone is 2 carbons away, it's at the beta carbon, it does it automatically. If it's 1 carbon away, and Madison, I won't make you answer this question, I'll ask anybody else, what B vitamin do we need to incorporate if I want to decarboxylate an alpha keto acid? And Madison, you can chime in if you know it.
Vitamin B1.
Yay, Maria, very good. It's vitamin B1, right? We need to have TPP. That is what we're going to use when we need to remove CO2 from an alpha keto acid. Another Jeopardy question. What if you wanted to add CO2? What B vitamin do you need for that? And Maria and Madison are talking to each other. I can see the same window behind you guys.
Okay, I'm gonna take a stab at it. I don't know if it's gonna be right. I feel like it's either B7 or B5.
Ooh, okay. I will tell you that one of those answers is correct. Would somebody like to chime in?
Wait, what was the question again?
If you wanted to add carbon dioxide,
Oh, B7.
yes, which is also known as
Oh, no, I know it. Biotin?
very good. Yes, biotin. Okay, so all of those extra questions were not related to Madison's original question, which is what is the difference between an alpha keto acid and a beta keto acid? Now, what makes it complicated is many of our metabolites have more than one carboxylic acid group. So then it's like, well, which one am I talking about? Well, whatever one you want to talk about. But if you're going to eliminate, and that's another big picture question, if you're going to eliminate carbon dioxide always comes from a carboxylic acid. If it is a beta keto acid, it'll do it spontaneously. If it's an alpha keto acid, you need vitamin B1, and you're going to see the megamol for that. That is like the theme. That's the homolog. That's what we constantly see when we see decarboxylation of alpha keto acids, is we see that dehydrogenase multi-enzyme complex. Good question. And it allowed me to play Jeopardy for a little bit with you guys. Anything else?
I vote that we actually do a Jeopardy because I think that'd be fun.
I know. You know what I used to have? I used to have a like we would meet weekly, and it would usually be at like 9 or 10 o'clock at night. And it was like, well, what would generally happen is I would make myself available. We called it a study lounge. And I had all the students would just get together, and it was on Zoom because it was during COVID. And I was trying to like create community with our biochem students. And then I would be available, and they would sort of call me in when you guys were studying about something and needed some help. But it usually ends up that they would call me in sooner rather than later, and then we would just talk biochemistry, and it was a lot of fun. And I'd essentially study with them. So, yeah, I'd like to study with you guys. Madison's like, yeah, you'd probably be a good person to study with.
We should do Jeopardy and brew beer at the same time.
We do need to brew beer. We do need to do that. We
Wow.
will do that after break here. Yep. All right. Anything else? I don't want to keep you guys too late. And like I have not been getting enough sleep lately, so I need to finish up a few things. I know I haven't I haven't sent out my Sunday night summary for you guys yet, or my Gen Chem students. God, you just sit there, and I'm sure you guys did this too. I'm like, you can see the light at the end of the tunnel with break. Like break is just like 2 weeks away and 1 week away. Just get yourself to break. And then like break happened, and like literally like life broke. And now I'm at the end of break, where I legit thought for you guys, like I didn't go to Toronto, right? My husband and I were supposed to go to Toronto. That didn't happen. We sent David with another family to go to Cincinnati because I needed to be home to take care of Sam. It's like, and now we're here, like, and there's there's not a lot of breaks before the end. Although April's going to be really April's weird because of how late Easter is. And then I've got 2 conferences. Oh, that reminds me too. Anybody who's interested in Pennsylvania Academy of Sciences, make sure there should be a Google Doc that was circulated to sort of gather information about any students that are interested to go so that we can make sure we have appropriate number of hotel rooms that we book and transportation and all of that. So I'll be in touch with you guys. And I don't think any of you guys, oh, Maria, you're 409, right? You're a 409 student. Madison, you're a 409. No, yes? Yes, you're a 409 student. So we will start up relatively quickly, kind of having weekly things that we'll do. Oh yeah, Lee, you're a 409 student as well.
It's
Yeah.
senior sem, right?
Yeah, senior seminar. Yep. So that's going to start up. There's not anything that you need to do this first week other than, and I think I gave you guys a preview of it before. You're just going to need to give me like a 1-paragraph summary of here's what my seminar is going to be about. Just making sure that I know that everybody's like continuing their 410 project or whatever. So, all right. Sorry for that rabbit hole because for some that doesn't apply to everybody here.
Do we have a specific meeting times for senior seminar?
No, there is not. I will say the meeting time that you have on a weekly basis is going to be with your research advisor. I want to know that you are meeting weekly with your research advisor to sort of go over things. There are like little assignments that you'll have to do. There might be a TED Talk that I give you to watch, and I'm going to ask you, okay, how do you think about this as it relates to your research project? But the goal is just to give you some benchmarks and milestones so that you're not sitting there a week before your seminar and not having done anything. That's the goal, is that we avoid that. So we sort of give you little pieces to bite off and chew so that, you're that's how you tackle a big project, like, or a big sandwich, one bite at a time. All right. Anything else? All right. I will see you guys tomorrow. We're back at it. All right. We still have lecture tomorrow. We're going to keep going on with electron transport stuff. So I will see you guys tomorrow on that. Bye.
Thank you.
Yep.